Welcome to part 3 of Unit 13. In this part, we're going to focus on elastic collisions. I put the link in again to the PhET simulation just in case you wanted it. And this slide again, and one more time to fill it out. So remember, elastic collisions, both momentum and energy are conserved. That R doesn't look much like an R. So let's see if we can make it better. For inelastic collisions, momentum only is conserved. Okay. Remember that there are many different combinations of final velocities that can satisfy the conservation of momentum equation for a given input, if you will. But there's only one set that will simultaneously solve the conservation of momentum and conservation of energy equations for the elastic collisions. The first thing we're going to do for elastic collisions is we are going to do a derivation. And this derivation results in a formula on your equation sheet. It is number 26, the very last one, that has to be valid for elastic collisions and is easier to use than the full statement of conservation of energy. Now, this is a very generic setup. We have two objects, A and B, colliding, and we want to know what their final velocities are after the collision, assuming it's elastic. We're actually not going to find numbers here. As I said, it's to derive an equation. To start with, normally I would draw a picture, but we don't really have anything to go on. What we do know is that the initial momentum of the system has to look like the initial momentum of the two pieces. And the initial energy has to look like the initial energy of the two pieces. Let's see, I think it was the V that had the glitch. So let's try writing that one more time. There we go. And we can write a similar statement for the final momentum and the final energy. And that I there is supposed to be an F, and now it has glitched, so I'm just going to clean it up completely. VA final, and while I'm at it, I guess I'll clean up the 2 as well. Okay, we're going to start by looking at conservation of momentum. So initial momentum has to equal final momentum. That gives us that MA VA initial plus MB VB initial has to equal, oh, that is a plus sign that was supposed to be an equal sign. So let's try again. MA VA final plus MB VB final. Okay. Now what I'm going to do is I am going to rearrange this equation and move everything that has an A to one side and everything that has a B to the other side. And that seems like potentially an odd thing to do. And I'm not going to motivate this move in any other way than to say, I'm doing it because I know where I'm going in the math. And you're just going to have to trust me. Okay, lastly, I'm going to factor out the masses. Oh, and I keep trying to rewrite the m's, so let's try not rewriting the m's because we don't need them anymore. Okay. Notice that for A, it's initial minus final. I'm going to pull out a negative MB, which allows me to write this as VB initial minus VB final as well. So both of them have the same basic format. Okay, mark this equation. Star it, box it, circle it in yellow. I don't care how you designate it. Here, I'll circle, I'll star. We are going to need this. Oh, that star's not very good. Oh, well, you get the idea. We're going to need this equation in a minute. But for the moment, we are going to shift gears. And our shifting of gears is going to involve looking at conservation of energy. So initial energy has to equal final energy. Oop, that's a final. Okay, so here is our statement of conservation of energy. The first thing to notice is we have a 1/2 in every term, so it can cancel. The next thing I'm going to do is the same move I made for conservation of momentum and move all the A's to one side and all the B's to the other. So that leaves me with MA VA initial squared minus MA VA final squared equals MB VB final squared minus MB VB initial squared. And again, I'm going to factor out those masses. Oops. Okay. Now, I'm gonna pull an aside, and for the aside, I'm gonna switch colors so that I'm gonna try to switch colors. Here we go. For the aside, I'm going to remind you of this. If I have x plus y times x minus y, that results in x squared minus y squared when you FOIL it all out because the cross terms cancel each other. And notice what I have is VA initial squared minus VA final squared. So that looks like x squared minus y squared, if you will. And the same thing for VB. Okay. Now, there's also a little bit of magic. And I'm not going to explain the magic or discuss the magic. Other than to say that if you know vector multiplication, there is a process called a dot product, and what we're really doing is undoing a dot product here. And because of that, at this step, the velocities become vectors. Okay, it's because we're actually doing a vector multiplication or undoing a vector multiplication. Okay, so switching back to red, I'm going to write this as VA initial plus VA final times VA initial minus VA final. And the same thing on the other side. VB final plus VB initial okay. And now we're going to go to the next slide and we're going to make another aside. So switching colors again so that our asides are also in another color. So this aside is, remember, you can do anything to one side of the equation as long as you do it to the other. So I'm just going to make up a sample equation and show you this. So if I do 2 plus, let's not do 2 plus 3. Let's do 2 times 6 equals 4 times 3. Okay. That's true. 12 equals 12, right? Now, I can divide both sides by a factor of 4. And you're thinking, well, sure, why can't you do that, Dr. Murphy? That works. But what if I write my factors of 4, say on this side I write it as 4 times 1, and on this side I write it as 2 times 2. Am I still doing the same thing to this equation? Yes, I'm still dividing both sides by 4, but the two sides now look different. Okay. So the next thing I'm going to do is I'm going to take the equation we were at the previous slide, and forgive me, I got to go back and make sure I get it written correctly. It's VA initial plus VA final times VA, I think it's initial minus VA final. Did I get that right? Oop, wrong way. Yes. And that has to equal MB times VB final plus VB initial times VB final minus VB initial. Okay, that's just a restatement of this line here. And now I'm going to take and divide both sides of the equation by something. And the two somethings are equal, but they don't look the same. Okay, so what am I going to pull on? Well, remember, way back here, we have this equation we circled and we starred and we said, hey, we're going to need it later. This is what I'm dividing by. I'm going to take the A side and divide by the A side, and the B side and divide by the B side. So on the MA side, I have MA times VA initial minus VA final. I will go back and make sure I've written that correct. Make sure it all agrees. Yes. And on the B side, I had a negative MB VB initial minus VB final. Okay, well, I pulled out a negative sign. I didn't really need to, but that's okay. Notice on this side, mass A cancels, and VA initial minus VA final cancels. On the other side, mass B cancels, and then the minus sign times these velocities cancels those velocities. And now I'm left with just VA initial plus VA final equals VB final plus VB initial. And this equation has to hold true for all elastic collisions. We have one more small step on this, and that is just to put all the initials back on one side and all the finals back on the other. So VA initial minus VB initial equals VB final minus VA final. Okay, so now we're going to box this in, and we're going to make a note that this is equation, I believe it was 26 on your equation sheet, and it is valid for any elastic collision. Okay, so when you're working with an elastic collision, rather than starting with this, use that. So much easier because your velocities are no longer buried in these squares. Okay, so now let's do an example of this involving bumper cars. So bumper car A collides with bumper car B. We want to know what their velocities are after the collision. So we're going to begin by drawing our pictures. So here is the initial. So we have a 300 kilogram car moving at 3 meters per second, and a 400 kilogram car moving at 2 meters per second. And notice in this I defined to the right as positive. And then we don't know what is going on here yet. So we're just going to leave it generic. Okay, so now we can write our initial momentum is going to be 300 kilograms times 3 meters per second plus 400 kilograms times negative 2 meters per second. And when you multiply that all out, you get 100 kilogram meters per second. And our final momentum will be 300 kilograms VA final plus 400 kilograms VB final. Okay, I can now use conservation of momentum. P initial has to equal P final. So 100 kilogram meters per second. Ooh, that tried to be squared. I'm so used to writing seconds squared. There you go. Has to equal 300 kilograms VA final plus 400 kilograms VB final. Okay, well, we can't take this any further because we don't know either VA final or VB final. What we do know is that it is elastic. So we're going to go to the equation we just derived, VA initial minus VA final equals VB final minus VB initial. This is 3 meters per second minus a negative 2 meters per second equals VB final minus VB initial. 3 minus negative 2 is a whole lot like 5. It's actually exactly 5. Okay, and now I can solve for one of them. So I'm going to say VB final equals 5 meters per second plus VB initial. And now that I have this relationship, I can take this and plug it in right there. Okay, so we had 100 kilogram meters per second equaled 300 kilograms VA final plus 400 kilograms VB final. And now we're gonna substitute in 300 kilograms VA final plus 400 kilograms times the quantity 5 meters per second plus VA final. Okay, removing the parentheses. And now I can combine like terms. So I have a 300 kilogram VA final and a 400 kilogram VA final. So that's going to give me 700 kilograms VA final. I'm going to bring the 100 kilogram meters per second down to the previous line. And notice I have a 100 and a 2000. So when I bring the 2000 over to the other side, that gives me a negative 1900. And now I can solve for VA final equals negative 2.7 meters per second. Done. I can then plug back into the fact that VB final equaled 5 meters per second minus VA final, which gives me 5. Oh, this was a plus. 5 minus 2.7 results in 2.3 meters per second. So now we can come back to here and say that VA final is this way at 2.7 meters per second, and VB final will be this way at 2.3 meters per second. Okay, now we've made the statement that this has to hold true if it's elastic. So as our final bit, let's go and just check conservation of energy. So 1/2 MA VA initial squared plus 1/2 MB VB initial squared. And if you plug everything into that, you get 2150 joules. And afterwards, you put this into your calculator and you get 2151.5 joules. Okay. Are these numbers perfectly equal? No. But on the other hand, these numbers here were not exactly negative 2.7 and 2.3. There was some round off that happened along the way. So this small difference that you're seeing between the initial and final energies, and the fact that it looks like the final energy is actually bigger than the initial, this difference is a round off issue. Okay. We have one more elastic collision example. This one involves billiard balls. So rather than reading it all to you this time, I'm just going to start by illustrating it. We have the cue ball. The cue ball has about 170 gram mass and is moving at 6 meters per second. So let's do this. It doesn't say a direction, but it does say that it's colliding with a stationary 8 ball. So there's the 8. I know it should be black. That has 160 grams for its mass, and it's initially stationary. It says let it be one-dimensional, which is actually a very, very big help. And as before, we want to know what the final velocities are. So I'm going to use C for Q and 8 for the 8 ball. Okay, as before, I can write out my momentums. So I have 170 grams. So I need to convert that to kilograms. So 0.17 kilograms times 6 meters per second. Assuming this is my positive direction, plus 0.160 kilograms times 0 meters per second results in an initial momentum of 1.02 kilogram meters per second. My final momentum is not overly helpful at the moment because I don't know either final velocity, but we'll write it out anyway just so that we have it. Okay, now like in the last problem, the first thing we did was apply conservation of momentum. Instead of doing that first, this time I'm going to start with this formula. 8 initial. There we go. VQ initial minus V8 initial equals VQ final. No. Eventually I'll get the equation written down properly. V8 final minus V8 initial. So that gives me 6 meters per second minus 0 meters per second equals V8 final minus V8 initial. And now I'm going to solve for the final velocity of the 8 ball is 6 meters per second plus V8 initial. Okay. Now I can look at conservation of momentum and set 1.02 kilogram meters per second equal to 0.170 kilogram VQ final plus 0.160 kilogram V8 final. And now I'm going to take this, I wrote this wrong. We're going to fix it. So it's VQ initial minus V8 initial. V8 final equals, this should have been a VQ final. So I got to change this to Q final everywhere. That makes so much more sense. Okay, all better. Now I'm going to take this equation and plug it in down there. So I have 0.170 kilograms VQ final plus 0.160 kilograms times 6 meters per second plus VQ final. Okay, factoring out, getting rid of the parentheses, 0.16 times 6 is 0.96. Okay, I can now combine like terms. I have 0.170 kilograms VQ final and 0.16 kilograms VQ final. 0.17 plus 0.16 is 0.33 kilograms VQ final. And that has to equal, if I bring this down from above, the 1.02 kilogram meters per second minus 0.96 kilogram meters per second. So that equals 0.06 kilogram meters per second. So the final velocity of the cue ball is 0.182 kilo, ooh, too many kilograms there, meters per second. And now that I have this, I can come up here and say V8 final equals 6 plus 0.182 meters per second. So that's 6.182 meters per second. This concludes this part of Unit 13. In the next unit, we are going to look at multidimensional collisions.